lecture was our introduction to zones. Today what I'd like to do, and we used the example of Scotland to show isograds and index minerals. And so what we're going to do now is actually go into the major types of zones that occur. So this is a continuation of the last lecture. We're going to start off with Roman numeral 3, and we're going to talk about the simplest type of zones first, and those are contact metamorphism zones. These are, of course, contact metamorphism is related to intrusions, which provide a source for both heat. All right, so we have magmatic intrusions provide heat and fluids. And it's those heat and fluids that causes changes in the rock. Let's just draw a kind of schematic over here. It's not very well to scale. Here's some trees on the floor to show we're at the Earth's surface, and then underground we're going to put a magma chamber, all right? And then off to the right from that magma chamber, there's going to be a series of, there's going to be metamorphic reactions that are occurring. We're going to release fluids in blue from the magma, and we're also going to release a lot of heat. How do we draw heat? Let's make it like kind of glowing like the sun, okay? So there's our simple schematic. What we're going to say is that these contact metamorphic zones diminish. Let's say they have the intensity diminishes with distance. That makes sense, right? Diminishes with distance from the intrusion. The reason for that is because heat and chemicals have to diffuse away. So these are our controls that we're going to put down right now. What are the controls on contact metamorphism? Well, it's diffusion of material, and then it's also advection of material. What does advection mean? That might be new to your vocabulary. Well, it just means transport. It's kind of a fancy geologic word for transport. So we're going to be transporting these materials through fractures. It's like fluid flow. Let's even put that, let's say like flow transport. And then diffusion, of course, is just more of a solid state process. The other control here, besides diffusion and advection of heat and fluids, is going to be the properties of the country rock. This is going to vary with shale versus sandstone versus limestone. They're going to have different properties. They're going to have different amount of fractures. They're going to have a different amount of permeability. They're going to have different amounts of porosity, and that's going to affect how material flows. And as it creates alteration, we could imagine that there are these zones of higher to lower grade alteration going away from the intrusion. The whole zone of contact is called a contact areal. I'll spell it here. Contact areal. And what we're going to do here we're going to have C be our zone of alteration, which we've drawn in, and then what this zone of alteration is called the contact areal. It can be all sorts of different sizes. In really small environments, it can be only centimeters across. In big intrusions with high permeability and good advection, you can have that zone of alteration be centimeters to kilometers across. The types of rocks that are produced by contact, well, there's a whole host of different really interesting rocks some of them are very important to mining, and some are completely nondescript. We'll start with that type that's really boring. Number 1 is called hornfells. Hornfells is for the rocks that you basically can't identify. They are so, zoom out, not zoom out, zoom in, zoom in. There we go, fully zoomed. So hornfells is a rock that's entirely baked, and it tends to be a silicic protolith. So let's just call this baked silicate protolith. They're incredibly fine-grained to the point where they're almost glassy, and they're dark-colored because they're baked so much. What do they look like in person? Let's throw a picture of one here from Wikipedia. We can see just this very fine-grained rock. This is the type of material that you'd expect to find really close to the contact. Hornfels. Now, the other type of rock that you're going to find, right, and then the hornfels highest grade will be nearest the perluton, the finest grained, glassiest material, and then lesser the further away you get. Now, the second type of material that you'd expect to get in contact metamorphism is called a skarn. And skarns are the ones that can have some economic value attached to them, where you get interesting mineralogy that can be used for metal mining or even gem mining. Because what ends up happening here is that we have a calc silicate. These are like limestones or dirty limestones, protolith. So let's say calc silicate protolith is metamorphosed. This ends up releasing a lot of fluids. So there is abundant fluids in skarn production. And the fluids, I'm running out of space here, these are going to be H2O, but really the most important is CO2 that's being released from the calcite in the calc silicate. And it makes a lot of really interesting mineralogy. Let's say that, interesting mineralogy produced. Some very famous minerals that have not much value would be calcite and epidote. These are very prominent in skarns, but will also make a lot of things like gold deposits, silver deposits, and all sorts of interesting gem deposits may also be produced. So that's contact metamorphic zones. Let's go into the next type of zones, and these are called regional metamorphic zones. There's a number of these types. This is kind of the crux of metamorphic petrology, is to understand regional metamorphic zones. Anytime we use the word regional metamorphism, that is a synonym for orogenesis. And orogenesis is not the formation of ores, it's instead mountain building. All right, so these are all synonyms with each other. And so what these are going to do, these regional metamorphic zones, are the production of facies in response to tectonics. The most important of these, in my opinion, is called the Barrovian zones. Barrovian zones are the true mountain building produced zones. So we're going to say these are from mountain building. And so what we could do is we could have a sketch here. Here's our mountain, and it goes down. And of course, wherever there's a mountain, there's also a keel that goes deeper. And what we'll have, here's our suture zone between the two plates that are colliding into one another. And what's up happening, at least in the classic politic sequence, is a series of minerals that goes from chlorite at lowest grade to biotite, to garnet, to starlite, to kyanite, and then to sillimanite. And this is what our zones are defined by. These are our index minerals. And so isogrades would get dashed in on a geologic map between them. All right, so those are our isogrades. What would this look like in the actual event? Well, the chlorite would be forming at the shallowest conditions, right, the lowest facies, and sillimanite would be down here. And we have to fill in all the rest between. So let's see, we get biotite and garnet and starlite and kyanite. And then we could, if we were doing a drill core, we could put in all of our isogrades like this. Of course, what ends up happening is that erosion and exhumation brings these rocks to the surface and tilts them, and so we end up mapping them on a downward surface rather than through the earth. But that's a later effect. So what we're going to say here is that this is our classic politic sequence. We could do a similar sequence for mafic rocks or carbonates, but for teaching purposes, we'll just leave it here with the politic sequence. We'll just do one little small note underneath this. Let's put this as number 1, and then under 2, we're going to just make a note to ourselves that these are now exposed at the Earth's surface. Now exposed at Earth's surface in ancient mountain ranges. right? Where we can walk on the core of some ancient mountain range. For example, in the East Coast, you can walk on the core of some of the Appalachian Mountains that formed millions of years ago. In Texas, where we go see what's called the Grenville orogeny, and we walk on some of those rocks when we're out in Llano, Texas. All right, so we can look at all these famous ancient orogenies. The second type of zone that is very important when it comes to big tectonic zones are called Buckin zones. And Buckin zones are very different than Barrovian. They're much more temperature dependent, not pressure. They're kind of like a regional scale. Let's even put that down. They're a regional scale contact metamorphism. They're not exactly contact metamorphism, but they're kind of similar to it. So I'm going to put like the approximate sign in front. And the reason why is because Buckin zones, put the definition here, they occur from fast rise in temperature in T at low pressures. In fact, the pressures tend to be less than 12 kilobars. And that's not right. 12 kilometers is what I meant. So let's put in 4 kilobars. These are shallow or crustal conditions. It produces things like, so let's say produces high T, low P minerals. And the minerals, these are things like andalusite and cordierite. When you find them in the rocks, they are typically randomly oriented because they're not in response to some kind of pressure event. Right? So let's also even say that when we see minerals that are randomly oriented, they might be Buckin minerals. How would we draw this? Well, we have to have tectonic environments where you get a lot of heat. So maybe we have an extensional environment where that extensional environment has produced a lot of magma chambers that are intruding over millions of years. And what that'll do is raise the geothermal gradient. Right? So maybe higher geotherm than what you'd normally expect is produced. And then the final type of zone to talk about that's related to tectonics is called the Franciscan zones. Named after San Francisco area of California, where it is certainly recognized. And basically the pattern that we see in California, let's draw California. Ooh, I should have drawn this a little, okay. Hold on. Let's do the eastern side of California a little better. So this comes up and then jags up there, okay. And then here's San Francisco, right? Well, what we end up seeing is in eastern California, there's this huge mountain range. This is the Sierra Nevada. And the Sierra Nevada is a series of plutons and batholiths from subduction. And what we see on the coast of California, through here, is a bunch of serpentine and blue schist. Serpentine and blue schist. This is called a paired metamorphic belt. And this is common in Franciscan zones. And so at Franciscan zones, we're going to say we observe paired belts. And the type of pairing that we see are arc magmas with metamorphic subduction zone rocks. And that's what serpentine and blue schist are. Metamorphic subduction zone rocks. That's our primary observation. The cause for this is very low temperature, very high pressure. This is the tectonic temperature and pressure regime. So what we have here is a very cold geotherm. That would be another way to say that. What causes the cold geotherm? Well, it's all about the subducting plate. So we're going to say this. We're going to say the downgoing subducting slab, chills the region. It acts as this ice cube that keeps everything colder than it should. Let me draw a picture of this for you. Here is our subducting slab, which is our protolith, I suppose, and here's our overriding plate with our volcanoes. And so what happens is, of course, here's where we have our magmas, and here's where we form serpentinite from our protolith, and here's where we form, so there's serpentinite, here's where we form, we're going to call that, here's where we form our blue schist, and even deeper down we'd form our eclogite. So when we see these two things near one another in some exhumed terrain, we'll say, this is most likely to be a Franciscan zone. So let's say mafic protolith. So in the end, what we have are 3 different types of zones that are all related to plate tectonics. If we go back to our facies diagram that we're using this semester, you could draw this in right now, or you could just, actually just go ahead and draw it in. What we're going to do is superimpose on this our different zones. Going through kind of this path right here, this is our Barovian zone path, where we have a normal geotherm of around 25 C per kilometer. Our Buckin style is hot but low pressure. So this is going to be our Buckin pathway. And then where would we put in our Franciscan zone path? Well, it's very cold because it's chilled by the slab. Oops, that's not the right place. Let's see, I want it to go from here. Oh man. Go here, up through blue schist, and up through eclogite. And we're going to call that our Franciscan zone path. All right, it's all about the geotherm in each of these examples. Cold geotherm, normal geotherm, hot geotherm.